Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The discovery of a planet orbiting a solar-type star, as reported by Michel and Didier Queloz in their 1995 publication, represents a pivotal moment in the history of astronomy. This essay undertakes a detailed evaluation of the central claims and methodologies presented in that seminal work, examining the evidence, analysis, and conclusions reached regarding what would become known as 51 Pegasi b. The subsequent sections will dissect this work, focusing on the validity and implications of each argument put forth, and contextualizing the paper within the broader scientific landscape. The intention is to provide a comprehensive and critically informed assessment of the impact and legacy of this groundbreaking research. Section 1: Introduction and Observation Overview. The paper begins with an introduction framing the search for extrasolar planets as a long-standing goal within astronomy. The authors emphasize the difficulty of direct observation, owing to the faintness of planets compared to their host stars and the close angular proximity between the two. And Queloz then transition to describing their radial velocity measurement technique, which exploits the Doppler effect to detect stellar wobble induced by an orbiting planet. This section is largely descriptive, outlining the observational setup and the underlying physical principles. The central claim revolves around the feasibility and precision of their radial velocity method, allowing for the detection of planetary companions via subtle shifts in the stellar spectral lines. The strength of this claim rests upon the established understanding of stellar physics and the Doppler effect. The author's careful calibration and error analysis, which they hint at in this introduction, will be of critical importance in later sections. They acknowledge the challenges inherent in the method, such as discriminating planetary signals from intrinsic stellar variability, a crucial point for later consideration. Section 2: Spectroscopic Observations and Data Reduction. And Queloz dedicate a substantial portion of their paper to detailing the spectroscopic observations performed at the Observatoire de Haute-Provence utilizing the Elodie spectrograph. They describe the acquisition of spectra for over 140 stars, including the target star 51 Pegasi. This segment is crucial as it establishes the foundation for all subsequent conclusions. The authors detail the process of data reduction, accounting for instrumental effects and calibrating the wavelength scale. Their primary claim here is the ability to achieve high-precision radial velocity measurements on the order of 13 meters per second. This precision is essential to detecting the small stellar wobble induced by a Jupiter-mass planet in a close orbit. Evaluating this claim requires assessing the error budget and the rigorousness of their calibration procedures. The statistical significance of the radial velocity variations hinges upon attaining this reported precision. Notably, I mention the use of thorium-argon lamps for wavelength calibration, a standard technique. The paper's claim is substantiated by a description of the data reduction pipeline, detailing the steps taken to remove instrumental signatures and extract reliable radial velocity measurements. Section 3: Radial velocity variations and the planetary hypothesis. This section presents the core evidence for the existence of an orbiting planet around 51 Pegasi. And Queloz showcase the periodic radial velocity variations they observed, characterized by an amplitude of approximately 57 meters per second and a period of 4.23 days. They interpret this sinusoidal variation as evidence for a planetary companion inducing a reflex motion in the star. This constitutes their primary argument. The observed radial velocity variations arise from a planet. This argument is presented strongly, with the data points clearly displaying a periodic oscillation. However, this section also requires the most critical scrutiny. Alternative explanations, such as stellar pulsations or star spots, must be convincingly ruled out. The authors acknowledge this and state that stellar activity is unable to mimic the observed radial velocity curve. They do not fully elaborate on the specific tests conducted to reach this conclusion within this initial publication, which necessitates later research and independent verification. The claim's validity relies heavily on their ability to demonstrate, conclusively, that the signal is not intrinsic to the star itself, a challenge they acknowledge. Section 4 Orbital Parameters and Mass Estimates. Having established the presence of a periodic radial velocity signal, the authors proceed to estimate the orbital parameters and the mass of the putative planet based on the radial velocity amplitude and the orbital period. They derive a minimum mass for the planet of approximately 0.47 Jupiter masses, assuming random inclination. They emphasize that this value represents a lower limit, as the true mass depends on the unknown orbital inclination. The authors posit that the orbit is likely circular, given the sinusoidal nature of the radial velocity curve. Here, the core claim involves the derivation of the planet's minimum mass and orbital characteristics based on the observed radial velocity curve. Assessing this claim involves evaluating the validity of their assumptions, particularly the assumption of a circular orbit. While their radial velocity curve appears sinusoidal, there could be slight deviations not initially detectable. Furthermore, the uncertainty in the stellar mass also propagates to the planet's mass estimate. Notably, the authors state the star is assumed to be similar to the Sun. A refined estimate would depend upon future direct measurements. The mass calculation depends upon a number of other astronomical values themselves prone to error. This will detailed. Section 5 Discussion and Implications for Planet Formation. In the discussion section, Mayer and Queloz explore the implications of their discovery for planet formation theories. They acknowledge that the close proximity of the planet to its host star is surprising, given conventional models of planet formation, which predict that gas giant planets should form at larger distances. Beyond the ice line, they suggest that the planet may have formed further out and subsequently migrated inwards through gravitational interactions with the protoplanetary disk. This section features speculative arguments that attempt to reconcile their observations with existing theoretical frameworks. The arguments here lack the direct support of the previous sections, instead relying on inference and tentative scenarios. The primary claim involves challenging the established understanding of planet formation and proposing a migration mechanism to explain the planet's peculiar location. The validity of this claim hinges on the plausibility and consistency of the proposed migration scenario. The author's suggestion of planetary migration, while groundbreaking in its time, has since become a cornerstone of planet formation theory. They correctly identify the need for revising existing models. They also draw attention to the potential prevalence of such planets around other stars, suggesting that their discovery may be the first of many. Section 6 Ruling out stellar activity as the source of the signal. While Mayer and Queloz briefly touch on the possibility of stellar activity mimicking the observed radial velocity signal, a more detailed examination of this issue is warranted. It is crucial to explore in greater depth the methods they employed to rule out this alternative explanation. One powerful technique involves analyzing the shape of the stellar spectral lines. Stellar activity, such as star spots, can broaden and distort these lines, leading to apparent radial velocity shifts. The absence of such distortions would strengthen the case for a planetary origin. Another approach involves monitoring the star's brightness for periodic variations associated with stellar rotation. If the observed radial velocity period matches the star's rotation period, it would suggest a connection to stellar activity. Mayer and Queloz assert that the observed signal does not originate from stellar activity, but substantiating that assertion calls for a more detailed examination of the relevant evidence and analysis. It necessitates a further dissection of stellar phenomena and how they differ from the planetary hypothesis. Section 7 High Precision Radial Velocity Measurements, a technical deep dive. The success of Mayer and Queloz's discovery hinged on their ability to achieve extraordinarily precise radial velocity measurements. A closer examination of the techniques and instrumentation they employed is essential. The Elodie spectrograph at the Observatoire de Haute-Provence played a central role. This instrument was designed to minimize systematic errors and provide stable, high-resolution spectra. The author's use of thorium-argon lamps for wavelength calibration was a key aspect of their precision. These lamps provide a rich spectrum of emission, lines that serve as a stable reference for determining the wavelength scale. Furthermore, sophisticated data reduction techniques were crucial for removing instrumental signatures and extracting accurate radial velocities. This section explores the intricacies of achieving the required precision. The authors claim to have reached 13 meters per second of precision requires significant validation of technical details. Section 8. The significance of a short period. Massive planet. The discovery of a Jupiter-mass planet in a short period orbit challenged conventional wisdom about planet formation and migration. This section delves into the theoretical implications of this finding. Standard planet formation models predict that gas giant planets should form at larger distances from their host stars, where it is cold enough for volatile ices to condense. The presence of a hot Jupiter so close to its star raises fundamental questions. How did it get there? Mayer and Queloz propose planetary migration as a possible mechanism, but other possibilities exist. One alternative involves in situ formation, where the planet forms directly from the protoplanetary disk at its current location. Another possibility involves gravitational interactions with other planets or stars in the system. Assessing the possible origin requires investigating the planet's composition and dynamic environment. Section 9. Confirmation and subsequent observations of 51 Pagars. Following the initial publication by Mayer and Queloz, numerous independent observations confirmed the existence of 51 Pagars CB. These confirmations played a crucial role in establishing the credibility of the discovery. Other research teams using different telescopes and spectrographs were able to detect the same radial velocity variations, strengthening the case for a planetary origin. Furthermore, subsequent observations provided more detailed information about the planet's properties. For example, measurements of the planet's radius using the transit method revealed that it's a bloated gas giant with a density lower than that of Jupiter. This provided further constraints on the planet's composition and internal structure. The process of verification requires close examination of subsequent observations, as they support the original argument. Independent verification is integral to the scientific method. Section 10. Constraints on stellar properties and the impact on planetary mass estimates. Accurate determination of stellar properties, such as mass and radius, is crucial for estimating the mass of the orbiting planet. The initial estimate of 51 Pagars' mass relied on assumptions about its similarity to the Sun. Subsequent studies have refined these estimates, providing more precise values for the star's mass and radius. For example, astroseismology, the study of stellar oscillations, has provided valuable insights into the star's internal structure. These refined stellar parameters impact the estimate of the planet's minimum mass. A more massive star would imply a more massive planet, and vice versa. This section explores the impact of refined stellar parameters on the planet's mass. The impact is important, as this will modify the arguments of the initial paper. Section 11. Investigating orbital stability and dynamical interactions. The close proximity of 51 Pagars CB to its host star raises questions about the long-term stability of its orbit. This section investigates the dynamical interactions that could affect the planet's orbit. One possibility involves tidal interactions between the planet and the star. These interactions can circularize the orbit and synchronize the planet's rotation with its orbital period. Another possibility involves gravitational interactions with other planets in the system. While no other planets have been directly detected around 51 Pagars, the presence cannot be completely ruled out. Such planets could perturb the orbit of 51 Pagars b, leading to instability. This section investigates the factors affecting long-term orbital stability. The original paper does not address such potential factors, and this section is warranted to examine them. Section 12. Atmospheric studies and the search for transits. The discovery of transiting exoplanets has opened up new avenues for studying exoplanetary atmospheres. When a planet passes in front of its host star, it blocks a small fraction of the star's light allowing astronomers to measure the planet's radius and probe its atmosphere. Although 51 Pegasi b does not transit its host star, the search for transits was a key goal in the years following its discovery. While no transit has been detected, atmospheric studies have been conducted using other techniques. For example, observations of the planet's thermal emission have provided information about its temperature and atmospheric composition. This section explores atmospheric studies and the search for transits and what they imply. The transit method would need to be employed to further refine values for the planet. Section 13, Refining Planet Formation Theories in Light of 51 Pegasi. The discovery of 51 Pegasi b had a profound impact on planet formation theories. Previously, it was believed that gas-giant planets could only form at larger distances from their host stars. The existence of a hot Jupiter so close to its star challenged this conventional wisdom and prompted theorists to revise their models. Planetary migration has emerged as a leading explanation for the origin of hot Jupiters. This scenario involves a planet forming further out in the protoplanetary disk and then migrating inwards due to gravitational interactions with the disk or other planets. This section examines how planet formation theories have been refined in light of 51 Pegasi b. This necessitated a significant shift, and the original paper set the stage. Section 14, The Role of Selection Effects and Observational Bias. It is important to consider the role of selection effects and observational bias in the discovery of 51 Pegasi b. The radial velocity method is most sensitive to massive planets in close orbits around their host stars. This means that planets like 51 Pegasi b are easier to detect than smaller, more distant planets. As a result, the sample of known exoplanets may not be representative of the true population of planets in the galaxy. This section discusses the limitations of the radial velocity method and the potential for bias. This is a significant consideration when analysing any scientific result. The original paper made no claim of the generalisability for all planets. Section 15. Alternative explanations revisited stellar oscillations and magnetic activity. While Mayer and Queloz presented compelling evidence for a planetary origin of the observed radial velocity variations, it is essential to periodically revisit alternative explanations. Stellar oscillations, or pulsations, can cause radial velocity shifts that mimic the signal of an orbiting planet. Similarly, magnetic activity, such as star spots and flares, can also produce spurious radial velocity variations. This section reevaluates the possibility of stellar oscillations and magnetic activity contributing to the observed signal. The possibility of these phenomena must be evaluated periodically. Section 16, Comparing 51 Pegasi b to other hot Jupiters. Since the discovery of 51 Pegasi b, hundreds of other hot Jupiters have been detected. Comparing 51 Pegasi b to these other planets provides valuable insights into the properties and formation mechanisms of this class of exoplanets. Some hot Jupiters are tidally locked to their host stars, meaning that one side of the planet always faces the star. This can lead to extreme temperature differences between the day side and the night side. Other hot Jupiters have highly eccentric orbits, suggesting that they may have undergone gravitational interactions with other planets in the system. This section puts 51 Pegasi b in context with other similar planets. Placing it in this greater context helps further refine planet formation models. Section 17, The Legacy of 51 Pegasi b and the Exoplanet Revolution. The discovery of 51 Pegasi b marked the beginning of the exoplanet revolution. Prior to this discovery, the existence of planets orbiting other stars was purely theoretical. The confirmation of 51 Pegasi b opened up a new field of research and inspired astronomers to search for planets around other stars. Since then, thousands of exoplanets have been discovered, revealing a diversity of planetary systems that far exceeds what was previously imagined. 51 Pegasi b served as a catalyst, sparking intense interest and investment in exoplanet research. The initial paper has a legacy of spurring innovation, as well as confirming theoretical models. Section 18. Advancements in spectroscopic techniques and instrumentation. The search for exoplanets has driven significant advancements in spectroscopic techniques and instrumentation. New spectrographs with higher precision and stability have been developed, allowing astronomers to detect smaller and more distant planets. Furthermore, sophisticated data reduction techniques have been developed to remove instrumental signatures and extract faint planetary signals. Techniques such as high-resolution spectroscopy and adaptive optics have also played a crucial role in exoplanet detection and characterization. These methods are required to increase the likelihood of finding additional planets in the future. Section 19. Future directions in exoplanet research. The field of exoplanet research is rapidly evolving, with new discoveries and advancements being made every year. Future directions in this field include the search for Earth-like planets in the habitable zones of other stars. These planets are considered the most likely candidates for harboring life. Furthermore, astronomers are developing new techniques for characterizing exoplanetary atmospheres, searching for biosignatures that could indicate the presence of life. Future study will focus on the composition of planets. Section 20. The ongoing pursuit of understanding planetary origins. Despite significant progress in recent years, many fundamental questions about planet formation and evolution remain unanswered. How common are planets in the galaxy? What are the typical properties of planetary systems? How do planets migrate and interact with each other? What are the conditions necessary for the formation of habitable planets? These are just some of the questions that scientists are currently grappling with. The pursuit of answers to these questions will continue to drive exoplanet research for many years to come. The original paper sparked this era of scientific inquiry. The paper set the stage for answering numerous questions. Section 21. The philosophical implications of exoplanet discovery. The discovery of exoplanets has profound philosophical implications. The existence of other worlds raises fundamental questions about our place in the universe. Are we alone? Is life common in the galaxy? The answers to these questions could have a profound impact on our understanding of ourselves and our relationship to the cosmos. The broader implications are beyond scientific and reach into philosophical questions regarding our place in the universe. Section 22. Summary and lasting impact of Mayer and Queloz findings. The 1995 publication by Michel and Didier Queloz detailing the discovery of 51 Pegasi B stands as a monumental achievement in the history of astronomy. Through careful observation, rigorous analysis, and insightful interpretation, they provided the first concrete evidence for a planet orbiting a sun-like star, forever changing our understanding of planetary systems and our place in the universe. While subsequent research has refined our knowledge of 51 Pegasi b and other exoplanets, the original work remains a cornerstone of the field, serving as a testament to the power of scientific inquiry and the boundless potential for discovery. The paper's enduring legacy is found in the revolution it kindled, prompting a paradigm shift and setting the stage for the ongoing exploration of worlds beyond our solar system and the continued quest to understand our cosmic origins.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.